Assalamu alaikum. We know a branch of physics that deals with the study of charges and its relation with the magnetic field produced by them when they are in motion is referred as electrodynamics. The entire concept in electrodynamics can be explained with the help of four equations referred as Maxwell's equation. Maxwell's equation give the behavior of electric charge and electric current, and apart from that it also give properties of electric field and magnetic field. Now these equations can be written in integral as well in differential form. The differential form of Maxwell's equation is beyond the level of higher secondary physics. So in this video we will discuss only about the integral form of Maxwell's equation. Okay. Now before going ahead, let me write these equations one by one. Maxwell's first equation. Now these four equations are just similar to Newton's equation of motion in mechanics. Now remember this first equation. So what does it say? Maxwell's first equation is nothing but Gauss' law in electricity. What is this? It is nothing but Gauss' law in electricity. Okay, let's see what it is. What does it say? Now, this we have studied in the first chapter. It says that surface integral of electric field over a closed surface is equal to 1 upon epsilon naught times the charge enclosed by the closed surface. Okay, repeat. Surface integral of electric field over a closed path or closed surface is equal to 1 upon epsilon naught times the charge enclosed by the surface. Here epsilon naught is permittivity of a free space. Now this we have studied in electrostatics. And Q is this one. Q enclosed is the charge enclosed by the surface. Now what do we understand from this equation? Now this equation relates, actually this gives us net electric flux. Electric flux means number of electric field lines passing or crossing through a given area. It's referred as electric flux. So it relates net electric flux with the net charge enclosed by the surface. Okay, this is what do we understand from this. Now apart from that, this equation also implies that electric field lines start from positive charge and ends at a charge. So they start from positive charge and ends at a negative charge. So what does it mean? It means that these electric field lines do not form a continuous closed path. Okay. Now from this we understand there is possibility of the existence of isolated charges. Now we can have separate positive charge and as well negative charge. So suppose I take a positive charge. A positive charge. This positive charge will have a electric field around it. Now, this is the electric field. The electric field of the positive charge. In a similar way, the electric field produced by the negative charge is given as this manner. They just act towards it. Now, this is the electric field produced by a negative charge. You can see the difference. Both appear similar to each other, but only one difference is electric field lines act away from the positive charge, whereas here the electric field lines act towards the negative charge. Okay. So from this we understand that electric field lines start from positive charge and end at a negative charge, and they do not form a closed curved path. Okay. Because charges can exist separately. Fine. Now we'll go ahead and we'll talk about the second equation. Maxwell's second equation. Second equation. Maxwell's second equation is just similar to the first one, and it deals with the magnetism. So it is also referred as Gauss law in magnetism. Gauss law. Second Maxwell's equation is also referred as Gauss law in magnetism. In magnetism, we study about the magnetic property of substance, and we also learn about the magnets. Let's see how it is written. Next, we have to replace E with B to get a Gauss law in magnetism. Surface integral of magnetic field over a closed surface, a closed path, is equal to 0. Now here we have 0. What does it mean? It means that magnetic field lines start from north pole and ends at the south pole of a magnet, and here they form, these magnetic field lines form continuous closed path. Electric field line do not form continuous closed path, but it forms a continuous closed path. Magnetic field lines form continuous closed path. It means, suppose I have a magnet. A magnet has got two poles. This north pole, it is south pole. So it is also referred as magnetic dipole. Okay. Here, magnetic field lines start from north pole and ends at the south pole. Now this is known to us. Now what if I break a magnet? Now if I break a magnet, it is not possible to separate north pole and south pole. Now suppose if I break this, on breaking this kind of magnet, this north pole, this south pole, if I break it at the center, if you think that we can able to separate north pole and south pole, it is not possible. Okay, on breaking, what will happen? It will turn into two magnets, each having north and south pole. Or it will take a new form. Understand? So this equation clearly shows that there is no existence of monopole in magnet. Okay, no existence of magnetic monopole. Mono means single, and this end of the magnet is referred as pole. So magnetic monopole is not possible. This is what Maxwell's second equation tells us. Okay, so I'll go for Maxwell's third equation. Third equation. Maxwell's third equation is written as a line integral of electric field or a closed path. If I write L here, it means line integral. If I write S here, it means it is surface integral. Remember that. Over a closed path is equal to rate of change of magnetic flux. Rate of change of magnetic flux. So d by dt of phi b. Here phi b stands for magnetic flux and E stands for electric field. So Maxwell's third equation is nothing but Faraday's law. What is this? Faraday's law of electromagnetic induction. Now it plays a very important role, no? In the revolution of modern science. Here, if you look at this equation, you may find that it relates electric field with the change in magnetic flux. What is this magnetic flux? Now suppose I have a magnetic field line passing through a given area. Here, the number of magnetic field lines crossing this given area is referred as magnetic flux, represented by letter phi b. This is the letter as phi. It's phi b. Okay. Now this we have studied long ago. Alright. This gives the direction of magnetic field lines. Now, as I told you, Faraday's law of electromagnetic induction plays a very important role. It tells us how electric current can be generated by changing the magnetic flux. Okay, the working of dynamo is based on this only. Okay, now dynamo is used everywhere. If you want to generate electricity by converting one form of energy into it, then there you make use of Faraday's law of electromagnetic induction. Suppose if you take the example of a nuclear reactor or a thermal plant, or in case of a hydro electricity plant, in all these dynamos are used at the end, no? Which converts mechanical work into electrical energy. No? And the development of a nation depends on how much energy does it produce. We know that. So it plays a very important role in the modern revolution. Clear? The next fourth equation of Maxwell. Okay, Maxwell's fourth equation. Maxwell's fourth equation. What does it say? Maxwell's fourth equation says that line integral of a magnetic field or a closed surface. Currently speaking, Maxwell's fourth equation is a modified form of Ampere circuit law. What is Ampere circuit law? Ampere circuit law is nothing but this. The line integral of BDL or a closed path is equal to mu naught times the net current enclosed by the surface or by that path flowing in that closed path placed in that surface. Okay, this is nothing but what is this? It is Ampere's circuit law. Ampere's circuit law. This we have already studied. Now, Maxwell's fourth equation is obtained by doing certain small changes to Ampere's circuit law. So, it won't be wrong if I say that Maxwell's fourth equation is a modified form of Ampere's circuit law. Ampere's circuit law. Got it? Now, how it is modified? Let me tell you. It's known as integral, line integral of a magnetic field over a closed path is equal to mu naught times the conduction current plus mu naught epsilon naught d by dt of EDA. Okay. EDA. This is known as Maxwell's fourth equation. What do we understand from this equation? Let me tell you. Here, this equation relates a magnetic field with the conduction current and a displacement current. This clearly shows that conduction current and displacement current can able to produce a magnetic field. This is what we understand from the fourth equation of Maxwell. Understand? And what are the significance of Maxwell's equations in electrodynamics? Maxwell's equation in electrodynamics confirms the existence of electromagnetic waves. Now, these equations confirm the existence of electromagnetic waves. Now, in the last class we have studied about electromagnetic waves, radio waves, microwave waves, infrared rays, visible light, ultraviolet rays, X-rays, gamma rays. All these things come under electromagnetic waves. Now they will play a very important role in our day-to-day life. Okay. If we talk about radio waves, without radio waves and microwaves, communication is not at all possible. No. We are completely dependent on communication in every part of our life. And apart from that, whatever knowledge we have about the universe is only by the study of radio waves or electromagnetic waves that we receive from there. Okay, just by studying the spectra of any star, one can able to say the composition of that star. So this is the importance of Maxwell's equation. I hope the video is useful. If you have any kind of doubt relevant to the topic, kindly put your questions in the comment section. Thanks for watching.